What if I told you about a machine that had to be built loose so it could tighten up at the edge of space? An aircraft designed to leak its own fuel all over the runway on purpose. A plane whose skin glowed cherry red in the sky not from its engines but just from pure blistering speed. For over 30 years, this wasn't science fiction. This was the SR-71 Blackbird. This was a machine so far ahead of its time, it looked like it was part spaceship, part airplane. A vehicle so fast that when a pilot saw a missile launch warning, the standard procedure wasn't to dodge, it was just to hit the gas. This isn't just the story of the fastest jet ever built. This is the story of how a brilliant, secretive team of engineers at a place called the Skunk Works basically told the laws of physics and materials science to sit down and take notes. It's a story about solving problems nobody had ever faced before with solutions that are still legendary. How do you build a plane that can outrun a missile? The answer isn't just about power, it's about completely rewriting the rulebook. Context of creation. You can't really get the Blackbird without understanding the absolute tension of the Cold War. In the late 1950s, America's best spy plane was the U-2, a high-altitude glider with a jet engine. Its whole trick was flying high, way up at 70,000 feet where it was supposed to be untouchable. That illusion was completely shattered on May 1, 1960, when U-2 pilot Francis Gary Powers was shot down over the Soviet Union by a surface-to-air missile. That incident was a geopolitical earthquake. All of a sudden, flying high and slow wasn't a la carte anymore. The US needed a new spy plane, one that wasn't just high-flying but truly invulnerable. President Eisenhower went to one of aviation's greatest minds, Lockheed's chief engineer Clarence Kelly Johnson, with an impossible demand: build me a plane that cannot be shot down. Johnson and his elite Skunk Works team, Lockheed's top-secret design group, knew that altitude wasn't enough of a defense. The only sanctuary left was pure, unadulterated speed. The requirement was simple on paper but staggering in reality. The new aircraft had to fly faster than any missile fired at it and higher than any fighter sent to intercept it. The target was a sustained speed over Mach 3, 3 times the speed of sound, and an altitude above 85,000 feet. At those speeds, the known world of aviation just stopped. Normal airplane materials would melt, conventional engines would choke, and standard fuel would vaporize. The SR-71 wasn't just a new aircraft, it was a whole new category of flight. Kelly Johnson and his team weren't just designing a plane, they were stepping into the void. Challenge 1: Conquering the thermal thicket. The first and most terrifying challenge was heat. When an airplane pushes through the air, friction and compression heat its skin. At 2,000 plus miles per hour, this thermal thicket becomes less of an issue and more of a furnace. At a cruise speed of Mach 3.2, the Blackbird's skin would average over 600 degrees Fahrenheit, 315 degrees C. The leading edges and engine casings would get even hotter, soaring past 1,000 degrees. A normal aluminum airframe would lose its strength and just peel apart. So the problem was obvious and terrifying: how do you build a plane that can survive being cooked alive? The answer came from a metal more commonly found in Soviet submarines at the time: titanium. The Skunk Works team decided that over 90% of the Blackbird's airframe would be a special titanium alloy. It was strong, surprisingly light, and could handle the hellish temperatures of Mach 3 flight, but it brought its own set of gigantic problems. In the 1960s, the US didn't have enough of the ore needed to make the alloy. The world's main supplier, the very nation the Blackbird was being built to spy on, the Soviet Union. In one of the greatest ironies of the Cold War, the CIA had to set up a web of fake companies and third-party agents to secretly buy the titanium from the USSR, who had no clue they were providing the raw material for America's ultimate spy plane. The Soviets thought they were selling the metal for civilian uses, with one of the cover stories being that it was for pizza ovens. Getting the metal was one thing, actually working with it was another. Titanium was so tough it would shatter hardened steel drill bits, forcing Lockheed's engineers to invent new tools and techniques from scratch. The metal was also chemically reactive. If it got contaminated during welding, it would become brittle, meaning even the local tap water couldn't be used. Every process had to use distilled water. But the most brilliant solution was how they handled thermal expansion. The intense heat of flight made the titanium frame physically grow by several inches. A rigid plane would have torn itself apart. So Kelly Johnson's team did something that defied all logic: they built it loose. On the ground, fuselage panels were made with noticeable gaps, making the plane look almost unfinished. The wings were built with a corrugated accordion-like skin to let them expand without splitting under the stress. This led to one of the Blackbird's most famous quirks: it leaked. A lot. Those gaps for thermal expansion meant the fuel tanks couldn't be fully sealed on the ground. Before every mission, the Blackbird would sit on the tarmac, weeping its specialized JP-7 fuel. This wasn't a flaw, it was a feature. The plane only truly sealed itself when it was screaming through the stratosphere, where the intense heat expanded the airframe and closed the gaps. To top it all off, the plane was coated in a special black paint. While it looked cool and offered camouflage, its main job was radiative cooling. It was designed to radiate as much of that intense heat as possible away from the skin. Section 3, Challenge 2, an engine that breathes fire. Okay, so you have a plane that won't melt. Great, now how do you power it? The engineers faced a massive contradiction. To get off the ground and fly at normal speeds, you need a turbojet. But to fly at Mach 3, you need a ramjet, a simple engine with no moving parts that only works when supersonic air is rammed into it. A ramjet is useless at a standstill. A turbojet will choke and die at Mach 3. So how do you build an engine that's both? The answer was the Pratt & Whitney J58, one of the most incredible jet engines ever made. Officially, it was called a turbojet, but it was really a revolutionary hybrid, a turboramjet that physically transformed itself in midair. At takeoff and up to about Mach 2, the J58 acted like a fairly normal afterburning turbojet. The magic started as the Blackbird pushed past Mach 2.2. A massive movable cone at the front of the engine, called the inlet spike, would start to slide backward. It moved up to 26 inches to perfectly control the supersonic shockwave entering the engine, slowing the air down just enough so it wouldn't shred the compressor blades. But the real trick happened inside. Above Mach 2.2, a series of massive bypass tubes would open, bleeding huge amounts of air from the compressor and ducting it directly around the engine's core, dumping it straight into the afterburner. At this point, the J58 was no longer a pure turbojet. The core engine was just keeping things running, while the massive volume of bypassed air turned the afterburner into a giant ramjet. At its Mach 3.2 cruise speed, this transformation was so complete that the engine's core provided only about 20% of the thrust. The other 80% came from the inlet and the bypass system acting as a ramjet. It was an engine inside an engine. To light this monster of an afterburner at extreme altitudes, they needed another wild solution. Instead of a spark plug, the J58 used a chemical called trithylborane, or TEB. TEB has a very special property. It's hypergolic, meaning it explodes violently on contact with air. For every engine start and every afterburner ignition, a shot of TEB was injected, creating a brilliant green flash and a guaranteed light, no matter the speed or altitude. Section 4, Challenge 3, the lifeblood of the Blackbird. So you've got a heat-proof plane and an engine that breathes fire. What do you feed it? And how do you stop the pilot and all the electronics from cooking? The Skunk Works engineers solved all of it with one elegant, brilliant solution: the fuel itself. The heat was so intense that normal jet fuel would literally boil in the tanks. A new fuel was needed, one that was incredibly stable. Shell Oil developed a custom blend called JP7. It was more like a high-end oil than gasoline, so stable you could drop a lit match into a bucket of it and the match would just go out. This made it safe but also incredibly hard to light, which is why the explosive TEB was absolutely necessary for ignition. But the real genius was how the JP7 wasn't just power, it was the plane's lifeblood and its coolant. Before being sent to the engines, the fuel was circulated through a massive network of pipes. It flowed behind the hot titanium skin, absorbing the crippling heat from the airframe. It cooled the landing gear, the camera bays, the cockpit, and all the critical electronics. The fuel soaked up the heat, keeping the plane's vitals from failing. In this incredible system, a problem became a solution. The heat that threatened to destroy the aircraft was instead harvested by the fuel. By the time the JP7 actually reached the engines, it was already superheated, which actually improved its combustion efficiency. The very act of cooling the plane made the engines run better. It was a perfect, self-sustaining loop. Because it leaked so much on the ground, the SR-71 would take off with only a partial fuel load to save weight, and its first move was always to meet a special KC-135Q tanker to fill up before starting the mission. Section 5, the legacy of invincibility. With these breakthroughs, Lockheed didn't just build a plane, they built a legend. For over 2 decades, the SR-71 Blackbird was the ultimate intelligence tool. It flew missions over some of the most heavily defended places on Earth, including North Vietnam and North Korea, snapping high-resolution photos from the edge of space. Its performance remains breathtaking. In July 1976, an SR-71 set official world records for an air-breathing manned aircraft that have never been broken. An absolute speed record of 2,193.2 miles per hour, Mach 3.3, and a sustained altitude record of 85,069 feet. On its final retirement flight in 1990, an SR-71 flew from Los Angeles to Washington, D.C. in 1 hour, 4 minutes, and 20 seconds. But its most incredible legacy is its perfect combat record. During its entire service life, not a single SR-71 was ever lost to enemy action. It's estimated that over 4,000 missiles were fired at Blackbirds over the years. None ever hit. Pilots would see the launch warnings, and their standard response was simply to push the throttles forward and outrun the missile. In the high-stakes chess match of the Cold War, the Blackbird was the untouchable queen. CTA. The story of the SR-71 is an amazing reminder of what's possible when you give brilliant people the freedom to solve impossible problems. If you enjoy these kinds of stories about the engineering that shaped our world, consider subscribing to the channel and ringing that notification bell. We have plenty more incredible machines to talk about. Conclusion. The SR-71 was eventually retired due to its high operational costs, which could run up to $200,000 per flight hour, and the rise of advanced spy satellites. Yet decades after its last flight, the Blackbird endures as an icon. It sits in museums today, still looking like it belongs to the future. It's a monument to a time when a small group of engineers, led by the legendary Kelly Johnson, were told to build something that defied all limits. And they actually did it. It's a timeless testament to human ingenuity, a sleek black shadow that proved that with enough cleverness, even the sky has no limit.